Hello everyone, my name is Wang Chunrui, and we are fourth group. And today we are going to talk about the single supply, single-ended input to studio class AB differential output AMP. First, this paper introduces an amplifier circuit derived derived from the Barry-Gilbert micrometer topology. Its key feature is the ability to convert a single-ended input signal into a pseudo differential class AB current output under a single power supply. The circuit is entirely implemented using bipolar junction transitions BJTs and employs a current steering mechanism, allowing the output current to be automatically directed to the corresponding output output term, terminal based on the polarity of the input signal. This paper provides a detailed description of the circuit architecture, parroting principles, small single and large single behavior, improved impedance characteristics, as well as T-spice simulations and experimental results. Potential applications in high frequencies and wide dynamic range. Current mode current mode circuits are also examined. And then how it works. C1 serves as a decoupling capacitor which allows the potential at Q1 base to vary from the basic VBE with the Q1 diode connection. Q1 acts as a mirror to Q1 for positive input signals and the curse of for large negative inputs, while Q3 is a cascade under small single conditions and so resists large negative input currents. With ideal equal size transistors, all collector currents are equal and set by the base emitter voltages of Q5 plus Q6, which are determined by the current through R3 as obvious. When the input signal is large and positive, input current flows mostly through Q1, which acts as a transconductor and the cascade device, and Q3 becomes cut off as its emitter voltage rises. Q2 mirrors the Q1 character current through cascade device Q4, which sees a replica of the large positive input current as the positive output.
My name is Zhuo Binhong. I will do the circuit analysis and the simulation. Okay, let's check DC bias calculation first. And here is the bias network. It uses Q5 and Q6, and the value is about VB6 plus VB5 and plus I bias times R3. So the I bias equals V bias minus 2VB over R3. And the 6 transistors have the same DC biased voltage, so their collect current all are the same, and the value is about I bias. Next, we do the small signal analysis. We calculate the transconductance of Q1 to Q4, and the value is equals I bias over Vt. The input impedance of this amplifier is 1 of GM1 parallel with the 1 of GM3 because if we're looking into the emitter of Q3, it's about 1 of GM3, and Q1 is a diode connected BJT, so the value also can be approximate 1 of GM1. So the input impedance goes to 1 over 2GM equals Vt over 2I bias, and the output impedance for single-ended is about 100 ohm. Next, we need to calculate the output current. If Vin rises, then input current increases, and Q1, Q2 is a current mirror, so the collect current of Q2 increases, and Q4 and Q2 is a cascade, so the collect current of Q4 also rises. Then this ended is positive output. If Vin rises, then the voltage of the base and the emitter of Q3 will decreases. Then the collect current of Q3 will decrease. So this ended is negative output. And we know the collect current of Q1 and Q2 is GM times V in. And because the IC3 is the negative output, so it's minus IC1 equals minus GM V in, and the IC4 is positive ended, so the value is GM times V in. Then we can define the differential output current is the positive output minus the negative output. Then the value goes to 2 GM V in. And we notice that the input impedance is proportional to 1 over GM and proportional to 1 over IC. So the input impedance varies sharply with the magnitude of the input signal. And we will do the next part is do the input impedance improving. But we need to check the simulation first for this one circuit. And for the small signal input, the differential output and it looks like a straight line. Its linearity looks like very good. And for small signal inputs, all the BJT operate with an I bias collect current, like this figure, and the value is about 260 mA. And both Q1 and Q2 conduct I bias with the 0 point input current at this point, and as does the Q2 and Q4. So the circuit acts with a differential output from a single ended. And for small signal inputs, the circuit operates like a Class A output stage. And if the input is a large signal, for the large negative inputs, Q1 enters cutoff, and while Q3's collector sinks the negative output current. And for large positive input, Q1 enters because the voltage of emitter of Q3 goes to down, so and Q3 enters to cutoff, and Q1's collect sinks the input current, and Q1 and Q2 is a current mirror, so mirrors the current, and Q2 mirrors the current, which then Q4 shows the current to the output. So then This and for large signal input, the amplifier operates like a Class B offstage, and it is capable of delivering the high output current like this the result. And here is the total output, and we can see, and here is the crossover distortion. So yes, it looks like it looks like a Class B offstage. And let's do the input impedance simulation. We can see as Bin equals 0 volt, the input impedance has a peak, and for positive, it goes to 50.7 ohms. And if the large negative voltage input goes to about minus 2.29, then the input impedance increases sharply to about 145 ohms. So the input impedance needs to improve. And to improve the input impedance, we put also put the resistor to in the emit of all the VZTs, and the value of R1 is 23 ohms. All the emit resistance is 18 ohms, and the I bias use 512 milliampere. Okay, for small signal input, the input impedance looking into the pace is R1, and plus the two pace is looking into is a R3, and the Q3 is 1 of GM3, and here is 1 of GM1 and R2. So, and the two paths is parallel, so the input impedance equals R1 plus the two resistors is parallel, and because R1 and R2 and R3 is the same value, and GM1 equals GM3, so the input impedance equals R1 plus R2 plus 1 over GM over 2. Next, for large positive signal input, and for Q1, the Q1 is because the input signal is positive and is large, so Q1's GM becomes very big, and 1 of GM1 goes to 0, but Q3 enters cutoff, so 1 of GM3 goes to infinity. So the input impedance approximately equals R1 plus R2. For large negative signal input, Q1 enters cutoff, so 1 of GM1 goes to infinity, and Q3 is GM3 becomes very large, so 1 of GM3 goes to 0, like a short circuit. Yes. So the input impedance approximately equals R1 plus R3, and then R3 equals R2, so the input impedance is R1 can be equals to R1 plus R2, and the input impedance correct curve, it looks like a peak at Vin equals 0 volt. There's a peak is R1 plus R2 plus 1 over GM over 2, and for the signal goes to very large, for positive and negative, it goes to R1 plus R2. So let's check the simulation. For small signal input, the input impedance is curved look like this, and the I bias does not is not at a being equals 0 volt, and the circuit operates like a class A output, but its input impedance can be controlled. And for large signal input, the input impedance curve goes like this. Yes, it's a peak in the middle, and the value for the value at Bin equals 0 volt is about 56 ohms. And if the thing goes to 8 volt, the input impedance equals about 41 ohm. And yes, it's approximately R1 plus R2. And for negative 8 volt, it's also like the value. And so this for large signal input, for this amplifier, its input impedance becomes adjustable, and it also can delivering the high out current, and because the emitter resistance, so the circuit has high dynamic range, like the input voltage can be from negative 10 volt to positive 10 volt. It's a very high range, and the out current has no distortion. Yes, linearity is very high. That's the simulation of the circuit.
好，我是薛伟忠。Now, I would like to discuss several key aspects of this circuit, focusing on input impedance behavior, distortion characteristics, and practical significance. First, regarding the input impedance, this topology behaves quite differently from conventional amplifier in most traditional designs. The input impedance is assumed to be constant. In contrast, the input impedance of this circuit varies dynamically with the amplitude and polarity of the input signal, while remaining symmetric around the bias point. Under small signal conditions, the input impedance is mainly determined by the resistor network and the transistor small signal parameter Gm/1. As the input signal becomes larger, conduction gradually shifts to one side of the circuit, causing the effect of Gn/1 to diminish. As a result, the input impedance approaches a nearly constant resistive value at large signal levels. The behavior helps reduce nonlinear interaction with the source impedance and therefore lower signal-dependent distortion. Okay, next. The second important point is distortion and Class A or B operation. This circuit operates in a Class A-like mode for small signals, where both sides conduct the bias current, providing good linearity. For large signals, the operation transitions toward a Class B-like behavior, where the output current is steered to one side depending on the input polarity. This transition introduces a small amount of crossover distortion, which is observed in both simulation and measurement. However, increasing the bias current can effectively reduce the distortion at the expense of higher power consumption. This provides a clear design trade-off between efficiency and linearity. Okay. Another interesting aspect is the potential for harmonic control. Because the input impedance changes with signal level, it is possible under certain bias and component conditions to suppress specific harmonic components, creating what are known as harmonic nulls. This property is uncommon in conventional amplifier architectures and demonstrates the flexibility of this topology for high linearity applications. Okay, finally, from an application perspective, the circuit operates in the current domain, enabling high bandwidth and wide dynamic range with a single supply voltage. These characteristics make it well suited for RF front-end circuits, mixers, and high-speed analog integrated circuits. In conclusion, this work investigates a single supply amplifier topology derived from Barry Gilbert's micromixer architecture. This circuit converts a single-ended bipolar input signal into pseudo-differential current output through an efficient current steering mechanism. At small signal levels, the amplifier exhibits Class A-like operation with good linearity and symmetric output currents. As the signal amplitude increases, the operation smoothly transitions toward Class B-like behaviors. In improving efficiency while maintaining functionality under large signal conditions. In addition, the dynamically controlled input impedance helps reduce nonlinear distortion and provides additional flexibility for harmonic optimization. Overall, this topology offers an elegant and compact current mode amplifier solution. Its combination of single supply operation, high bandwidth, low power consumption, and pseudo-differential output makes it a strong candidate for modern high-speed and RF analog circuit applications, and an excellent example of innovative analog circuit design. Okay, and here is our reference. Okay, that's the end of our presentation. Thank you for your attention.